I'm leveling it.
The bot needs a little bit of babysitting.
Quite a bit, yeah. So sometimes I'll let it run for an hour or something, but during that hour, I probably have to spend 20 minutes with it.
Well, if you're like watching a movie or something and you're just like letting it go,
Yeah, that's it. But mostly I'm leveling by hand. Okay, so you had a homework assignment that was to look at how operating systems worked prior to multiprogramming, right? Okay, because as we've been seeing recently, as we're writing this little simulator, we have this issue where let me just make sure this is recording. Yep. We have this issue where lots of things need to be occurring at the exact same time using modern approaches to operating systems. So the CPU scheduler needs to be able to do stuff, separately from the process scheduler, and we can imagine that the memory manager probably needs to do stuff separately from the process scheduler, separately from the CPU scheduler. So how did operating systems work before we had the ability of forking processes and things like that to have multiple things running at once? What did we do? Nothing? We wrote a paper on this, right? So go back to like early DOS. So this is prior to multiprogramming. DOS allowed you to run one program at a time, right? So we have one user program, but then you also had the operating system running. So how did an operating system like that function, given the fact that running multiple things within the operating system at the same time wasn't really in the cards? How many of you were mentally already on break? Tell me what you wrote about. Abe, what'd you write about?
Didn't need to, for memory management, you didn't need to split that up into different sections. You just needed two sections, one for the operating system and one for the one program that you're about to run.
Okay. Why?
Because you could only handle one program. And it didn't need more than that.
Okay. So really you're saying that it has to do with the nature of what the operating system needs to be able to accomplish when we only have one program. So what we've been dealing with here in our simulation deals with context switching and all this stuff. When you have more than one program, you need to support it once, correct? So as we're moving things away from the operating system, moving things away from one process into another process, that requires all this communication between our various schedulers. When you only have one program running, well, we're not having to deal with that guy being interrupted, removed from the CPU. For I/O, by modern day standards, when there's an I/O interrupt waiting for something to happen, there isn't another dude waiting in line to get onto the CPU. So it was just acceptable that the CPU sits there idle while you wait for the I/O, right? What did the operating system do in the background, or did it do anything? So we got to think about the nature of operating systems back then. Today, we launch our operating systems and we, do the Control-Alt-Delete to look at Task Manager, and we can see all this stuff listed that's currently running. Similarly, on Unix, we've looked at top, where it shows us all of the current stuff that's running in the background that we know we didn't launch, that are part of the operating system. Was there stuff like that in earlier operating systems like DOS? So the operating system boots up. We're thinking about the DOS operating system. We're sitting at a command line, and we type in edit. So we're going to go run a word processor, something like that. Okay, so we type in edit. And now we're in the text editor. So the text editor gets loaded into memory. We're sitting there. Now we are working directly with the text editor. What's the operating system doing in the meantime? Nothing. Did it have to worry about process scheduling? It didn't have to worry about handling us double-clicking on a program, right? Or the predecessor to that, actually typing in a command. Okay, so it didn't have to worry about us typing an edit in another terminal window to launch a text editor a second time or something like that. Okay, so it didn't have to deal with creating new processes. Did the CPU scheduler have to deal with context switching away from the CPU? Only when an application ended. So when we went up to File and hit Quit for our text editor, at that point in time, that guy left the CPU, and who got control of the CPU again? Operating system, right? Now, realistically, was the operating system waiting in line? Or if you're writing that operating system, do you probably just launch the executable that is the shell? So that shell program, the thing that sits there waiting for user input, it's just a program, right? So when your current executable ends, when edit ends, the shell just gets relaunched. It's a brand new program, and now it's waiting for user input again. Why? Well, because that's probably easier than having to maintain a ready queue. Why have a ready queue when we didn't have to have a waiting queue for I/O? Because I/O we just waited on. Literally waited. The CPU didn't do anything. So that's an example of an operating system like DOS. Now, back then, when we had DOS running, these single programming operating systems, did we also have multi-programming operating systems from Unix? DOS was not the first operating system, right? Some other operating systems existed prior to DOS. Any of you read anything on some of those? Older versions of Unix? Did those have to have more than one program running at once? How did they handle situations where we weren't able to create multiple copies of a process? Hmm? Well, tell me what the timeshare thing is.
Little time allocation.
Okay, so each program got an amount of time?
Yeah.
Okay, so in our current model that we're writing here, that would be the kind of the communication between the CPU scheduler and the process scheduler, right? Okay, well, so can those guys be running simultaneously while our user program's running? So who's in charge of it? How would that work? Put yourself in the shoes of an operating system designer based on what we know in here. And we know enough. Based on what we know so far, how could you write an operating system like a Unix that supported multiple people launching a program at the same time? So almost the time period I'm thinking about here is dummy terminals. Computer labs back then, you would go into them and you would have a bunch of monitors sitting around with keyboards hooked up to them, and they'd be considered dummy terminals. They didn't have a CPU sitting there locally. They all hooked into a central computer, central box that was the terminal server for that guy, which then utilized a CPU on the back end. And we'll see if anybody noticed, because I may or may not have just given away some of the answer.
Each terminal got its own CPU.
What do you mean each terminal got its own CPU?
Well, since we weren't context switching between programs, that would mean that each CPU would have to be dedicated to a single program.
Okay.
So
We only have one CPU. So we're putting ourselves in the shoes of the developer of this operating system back in the day, so to speak. Okay? So this is prior to the internet. We didn't have people from Russia remoting into our server. We had people from across the room connected directly via cable to our server. Okay? Or, in the early days of local area networks, Token Ring or ArcNet networks, things that predated Ethernet. If you wanted to have a network that ran across campus, well, you're going to have long wires that run across campus. That's how it's going to work. Older networking things, and apparently, how many of you are taking 440 next semester? Is that the networking course? Apparently, I've been told I'm teaching that. So,
Is that an online class?
Historically, it has been, but I don't think it is this time. It was news to me. Oh God. It's actually not a bad class. It's kind of a cool class, but historically we've always just taught it remotely or taught it online. But if you're an IT major, I would strongly encourage you to take that class. Strongly encourage you to take that class. Computer science majors, take it. I think it's a good class regardless. But if you're an IT major and you don't take it, you're an idiot. Because that's what IT is. So you got to understand the networking world, and we talk about, we don't talk about how to set up a router. We talk about how routers work and things like that. When you get into IT and you have to maintain these things, and you become the Mark Newhouse character at some place where you are dealing with stuff behind the scenes that the end users just complain about. These are things you're going to have to know. So it's a good course. I don't particularly like teaching it, but I am good at it. So I'd rather just do it online because I could just point them to my old videos. So in any case, we don't have people utilizing the internet to remote in. We have everybody physically in one location. Put ourselves in the shoes of somebody who's developing that operating system. Okay, so we're writing that old Unix operating system that needs to support multiple users running multiple programs at the same time. Well, multiple users each running up to one program at the same time, utilizing a single CPU, because this predates multiple CPU machines as well. At least publicly available multiple CPU machines. There was probably some sort of secret government thing stolen from the aliens, but that's the whole. How many fingers did we decide they had? Is it just 4? 6. Lose count. 2 different races, probably.
4 because
Base 8, that's it, right? Or was it 8?
I don't think it was 8. I think it was.
Okay, makes sense. Yeah, I get confused. There's a couple of different species of aliens that we're aware of. So, yeah, watch a lot of those shows. Those are interesting shows. Like, documentaries, conspiracy theory stuff. Yeah, I think that stuff's cool. So, if there are, there are. If there are not, there's not. I tend to think there are. There's the old. How many of you seen the movie Contact? Jodie Foster, years ago. Really good sci-fi thing. We receive an alien signal. It was like a big blockbuster hit when it was out, sometime in the 90s probably. But she runs a radio telescope array that's listening for alien signals or whatever, listening to different stars for intelligence signals. They receive one, and basically they download a schematics to build something, and she goes and visits them. And it's really fascinating. It's interesting. It's kind of like what you imagine it might be like if it really happened. It wouldn't be like they send a ship to pick you up. It's something else. It's kind of interesting. It's worth watching. But there's a quote from the dad in the movie, the little girl who then grows up to be the Jodie Foster character, is out there looking at the stars with their dad and, asking, is there other life out there? And the dad's like, well, if there's not, it'd be an awful big waste of space. Well, I don't know. I think that's interesting to think about.
You should make a sci-fi movie in which they find out that it was actually Amish that they were doing it.
That would be great. That would actually be. If you could make that movie and properly market it, I really think a movie that tries to explain all this historical stuff and weird things that happened in ancient Egypt, if you can somehow connect that in this weird inadvertent way to the Amish.
We're gonna go back to the Illuminati.
All these like
The
secret.
Amish run the Illuminati.
Yeah, they're the founders of all this stuff, and now they go under the radar. We don't even like consider them as possible culprits. The original pharaohs were actually Amish. That'd be great. Okay, so in any case, if we put ourselves in the shoes of old developers, the people writing these old Unix operating systems, in that environment where we have a bunch of dummy terminals physically connected to the central server, and we don't have the ability to spawn off multiple processes. We don't have the ability of having a CPU scheduler and a process scheduler and all this stuff running at the same time. How do we solve that problem? So that's the, we're in a room back in the 1960s, let's say, and we're trying to come up with a solution to this problem. All of us right now. What are some things you might throw out?
Just have one operating system program running, and that fakes off multiple GUIs to the.
Okay, what do you mean fakes off?
Displays the material for each terminal
So,
number.
okay, so a shell on
Yeah.
each of the screens?
Yeah.
Okay, well, how's it going to do that? How, if there's 10 people using it at one time, how is it going to have 10 shells and be able to respond to input from 10 different shells?
Not quickly.
How does it, what is it going to wait for you and the dude next to you can't do anything until you're done? It's like, come on, quick, press enter. It's my turn.
You could have something on the terminal that allows a push, say, okay, I'm ready to send or I'm ready to receive something.
Okay, so this kind of comes down. Well, you guys did write a paper on this, right? So how come there's no answers? Like good answers. So we have the CPU itself. And then we have a bunch of dummy terminals. Okay, so there's our computer lab. Then we have our terminal server. All of these guys are linked here. Good enough. Okay, so all these dummy terminals are all hooked up through physical connections to this terminal server, this guy here in the center, which is a piece of hardware. So in this case, I have 6 dummy terminals. So this guy means it has 6 plugs minimum for this in this example. It has, usually back then it was parallel ports. Okay, so it's going to have, there'll be a parallel cable running from here to here. A separate parallel cable running from a separate port on this guy from here to here, so on and so forth. Okay? And we can go into the room over here and see that. We have one of those machines in there. And you'll see on the back of it, we have a whole bunch of parallel ports. Okay, or serial ports, depending on the vintage of the machine. Parallel being a parallel technology, serial being a serial technology, one bit after another, just different ways of handling the same thing. Okay, so this box here is going to have a bunch of ports on it. Each of these machines is plugged into a physically separate port. This box is then connected to the CPU. Now, this CPU might be a separate machine. This CPU might be housed inside of this piece of hardware. But whatever, this guy has a CPU. Okay? And we'll say in this example, a single CPU. So, this single CPU is doing all the work. And again, we have the limitation right now of dealing with we cannot create multiple threads. This is way before threads existed. We cannot create multiple processes and have the CPU schedule those, because in the middle here we have an operating system and as we've discussed in here, operating systems have all these parts, and as we've discussed recently, some of those parts need to be able to run at the same time for modern operating systems. So given this setup, if we couldn't have a CPU scheduler and a process scheduler, and we think about what each of those pieces do, what does a CPU scheduler do? It handles things getting time on the CPU and leaving the CPU. What does a process scheduler do? It handles launching individual applications, getting them into memory, and ultimately feeding them to the CPU scheduler. Each of these guys has a job, okay? And we cannot have, in software, that's the key word here, in software, we cannot have multiple workers working at the same time. So, we have to build it in hardware. We have a chip for doing the jobs of the CPU scheduler. We have another chip for doing the jobs of the process scheduler. Another chip for doing the jobs of the memory manager. Okay? So physical pieces of hardware that physically exist independently to each other. Not in software. Software didn't spawn off a copy of this program, a copy of this program, and a copy of this program. We have physical pieces of hardware that are physically running on their own. Okay? It's like their own machine, their own engine. Right? And those guys are sitting there doing the work that we take for granted today. And that's why we needed this terminal server in the middle. Does that make sense? Okay, so what did we do before we had threads and processes and multiple processes? We built it in hardware. If we need 3 dudes to do a job, we'll put 3 chips in there. Simplifying it by saying chips, but you get what I'm saying, right? Okay, so that's how we pulled it off. Now, as soon as the advent of the internet, where we didn't have all our machines sitting here locally, we couldn't have them all physically plugged into a single centralized terminal server. Well, now we have a new problem to solve. How do these guys connect? Well, so now instead of this being a physical cable, physically connecting it to this thing, now you might have a couple of these machines. I want new colors. Oh yeah. Man, I can't even use this computer now after using a 5K monitor on my Mac. Everything just seems so fuzzy. Well, if you didn't know, I got my 5K iMac yesterday. So now everything else is a paperweight. All right. So let's say these couple, those are pink lines. I can't tell, the monitor might as well be off. So we're going to say these couple of connections that are pink lines, these aren't local. Okay? These guys aren't sitting in the same computer lab or in the same building. These guys are somewhere out there on the internet, still somehow connected into this central guy here. This used to be a physical piece of hardware. What did we do over time? We had to build things into our languages that allowed the things that were happening through physical pieces of hardware here to happen in software in the operating system. Okay, so the operating system used to be split across software and hardware. And it's still the case, but we've abstracted large portions of the hardware portion into software. Now we think of our hardware portions as being the endpoints, the actual memory, the actual CPU, okay, the actual I/O devices. Those are the endpoints. Everything inside of that is, well, most things inside of that is software. The only thing that's not really is the connections, the wires that go between the CPU and the RAM. That kind of stuff. Those still exist in hardware, but everything else is driven by the software. And we rely on our processors to be really, really, really fast because historically, wouldn't you say, generally speaking, hardware is faster than software? Software is the middleman, right? So if you had a machine that had to do something, we think of software as being a convenience, but hardware as being fast. Just put eye drops in. Is psych going, old man? We determined that Alex is actually much older than he appears. He's not as old as me, but shockingly close. Almost 30.
So,
Well, I'm just saying, now I have a reason to make fun. Joints are going, his eyesight's not so good. Only gets worse. You're older than me, right?
oh,
How old are you?
I'm 43.
43. Oh my gosh, you are old. I'd be lucky to make 43. Yeah, that's the progression. So go from you to me, and then this.
Yep.
It's an empty husk.
Yeah, kinda.
Your problem's typing, and how's the vision?
Oh, yeah.
That's gone too?
Yeah.
Nothing. Took the glasses off here in the front row. Just like,
Yeah.
I don't even notice. The weight was hurting her ears.
Yeah.
much.
My prescription is changing like on a 6-month basis,
Yeah.
and these are old and they made me headachy.
Yeah, I know what you mean. I gotta like take my glasses off when I like read certain things. It's terrible. It's getting old. All right, so when these guys are off site, we need to have a way of processing this. And there is a new marriage between hardware and software. And when we think about building things that need to be fast, even today, we want large portions of it to be done in hardware. The more we can do in hardware, the faster it will be. It's hard coding it, if you will, is hardware. But what's the purpose of software? Upgrading it, right? When you buy a cell phone, you buy one of these smartphones, the day you get it, it's a certain piece of hardware. 2 years later, it's the same piece of hardware, right? But hopefully by today's standards, what's changed in that 2-year period is the software running on that hardware, working out some of the kinks, making certain things work better, making other things work worse, things like that. But that software gives us a level of flexibility to augment our hardware to make it work better, to extend the life of it, as opposed to having somebody come in and physically fix it, right? So think about like a house, and you have your water lines in your house. You know, if you have a problem with your water lines, you can't just go and download a patch, right? You got to have somebody who knows what they're doing come out and fix it, physically fix the lines. So that's where we were dealing with computers historically. Now we try to decide that balance. How much of it needs to be in hardware, how much of it should be in software, and where's that marriage for performance? Make sense? Okay, so questions about any of that? So hopefully that's what you would have kind of come out with your paper is this idea that we had hardware picking up the slack when software was lacking, which is why computers used to be bigger. You know, not just because of the transistor. You know, certainly before we had transistors, which were basically Boolean expressions in hardware, just call it that. Before we had those, we had the vacuum tubes for the Boolean expressions, and now things are a lot bigger. But you know, even after we had transistors in the early days of computing, our computers were significantly less powerful than they are today, and physically probably bigger, or at least no smaller than we have today. We think about our Mac Pro down the hall here. You know, it's probably the most powerful machine we have on campus as a single machine. Even the servers we have unless we have a newer server down there, but you know, it's certainly up there. And the thing is, I don't know, 4 times the size of this cup. It's not very big. It's like shockingly little. This looks like a, you know, like a travel mug is what it looks like. Super powerful computer with a bunch of cores in it, bunch of processors in there. Physical processors are in this thing. Well, you had machines with a millionth of the power and 10 times the size not that long ago. All right. Just for a little bit here, I want to pause our simulation thing because I want to make sure we get through some stuff. We'll bounce back to it after we introduce some memory. So I want to kind of turbo through this slide set and start the next slide set. Some of these things are going to be kind of fluff or things that I've already talked about kind of out of order compared to the book. So we've talked about a lot of scheduler stuff. So we kind of have our process scheduler selects which process should be brought into the ready queue, and then short-term scheduler selects which process should be executed next and allocate the CPU. So this is kind of telling us that process scheduler kind of has 2 individual pieces. One guy that's constantly going back and forth between what goes into the ready queue and another guy that actually is doing the job of loading things into the CPU. So we've advertised the process scheduler as kind of being this dude that's just always waiting for requests. That makes sense? And those requests come in a couple of different ways. One is who needs to get in the ready queue or who needs to get in the waiting queue. And the other one is I need another process now. I need a PCB now. Well, what this is saying is we actually divide that into 2 separate threads. One guy takes requests for PCBs. Another guy takes requests for putting people in line. Okay? All under the single umbrella of the process scheduler. Same crap. So this is the swap in, swap out, context switch crap with this medium-term scheduling. This is all just fluff for when you implement the process scheduler, you might implement it with multiple threads that handle different aspects of it. Relatively unimportant. We've talked about context switching a lot. Talked about process creation a lot, building it into a PCB, stuff like that. This part is a little bit helpful. So when we have child processes, whether it's a child thread or an actual physical child process as a result of a fork, Abe. So you might have a parent that creates a child, and those children might also create additional children. Okay, so you can have, you know, a big connection. Every process has a unique identifier for physical processes. If you have threads, they don't have unique identifiers across the system. They have unique identifiers within a single thread cluster associated with a single process. But processes on the system each have a PID, process identifier. If I go in here to the terminal, and I run top, we'll see the process IDs of all these things that are running. So these are unique phone numbers of all these different things that are running on the system. Okay?
Thought of Megan's MacBook.
Who? Yeah, that's a weird thing. Every time I get on the network, it picks up a different And it's not always this. Every time I change it, it changes. Every time I get on the network, it changes. And it's been for several versions of the operating system. Probably some sort of weird Bonjour bug or something like that. Bonjour is a Apple networking thing.
Fortunately, you couldn't access their stuff.
Well, you might be able to. Let's see if they show up in my my servers. Not there. Maybe I can map a drive. I don't think that's different. Well, let's look. Oh, there we go. Is Megan in here? Hey, these are like faculty. Here's Jennifer Delwich, faculty. This is a nursing faculty. Yeah, their machines just physically show up in there. Let's see about this Megan. Oh, that's not the same one, right? That was called Megan MacBook. Yeah, unrelated to this. Really seems like they should not have the machines publicly available, even though you can't access them directly. Because just having the names of the machine opens them up to a network attack. Whatever. So now we have something to do with the networking class next semester. Hack into other people's computers. So anyways, every process has a unique identifier. Processes share resources. Parent and children share all resources. So that's this actually has to do with inter-process communication. So parents and children share something called shared memory, a portion of memory that they both have access to. Children specifically share a subset of the parents' resources. So depending on, you can almost think of this at the software level. The child portion, if you have a program that forks, you usually have the fork command, which would then receive a process ID. If the process ID is 0, that means you're the original, you're the parent. If the process ID is something else, you're the new child that was just born. Then depending on that, you would have an if statement that says, if PID is 0, keep doing parent stuff. Else, it's not 0, it's a real process ID, it's a new unique process, do child stuff. And inside of there, you might have local variables, local resources that aren't accessible to the parent. That kind of stuff. Let's see, execution. Parents and children execute concurrently in a, this is specifically in a process where we use the fork system call. When we're creating threads, the parents and children actually, the child threads are sharing the resources, the CPU resource that the parent is given. And a parent won't terminate until the child terminates. So the parent has to wait for all of its kids to die before it can die. Okay. Same old crap. We've seen that a bunch of times. Diagram that talks about what we just talked about. Oh, PID is equal to 0? Doesn't seem right. So here's some C code. Here's where we call the fork system call. We capture the process ID associated with that. If the process ID is less than 0, that means something happened. We had a failed fork, Abe. That's a standard error. Standard error. So else if process ID is equal to 0, it's telling us that's the child process. I guess it's possible that my memory's failing me. I really thought that wasn't the case, but let's assume this is correct. So in any case, process ID being equal to 0 says it's the child. I would think that you would get the new process ID created from the child and you'd have access to that. And if it was you, you would still be a 0. But whatever, we have some process ID that indicates that we're the child. So for the child, we're going to say that we're going to execute the ls command. So ls command just as a directory listing. So if I type in ls right here, it's creating a brand new process, is this example, that runs on, gets its own CPU time and executes this command. And it already went to completion. Else, we're the parent process, so we're going to wait for the child to finish, and then we'll say child is complete, and we can end. Or we can loop back up, because realistically, if this is the parent's the shell program, and we type in ls, the shell program is going to wait for that child to finish. So I type in ls, I press enter, it gives me the directory listing, and then the parent is notified that the child finished, and then the parent can show the prompt again. Make sense? So that's kind of a real life example of what's going on behind the scenes. This is the code that kind of shows that. So this is an example of a Unix operating system called Solaris. So you have your scheduler, you have a bunch of programs that spawn off that. Off this program init, we have a bunch of programs that spawn off that. So inetd is the network interface. Telnet daemon is going to be the thing that looks like this to allow people to remote into the machine through a network protocol called Telnet. CSH is the name of the shell. So I think we're running bash here, but if I type in CSH, it'll give us something that looks similar, but this is the C shell. Get it? C shell. So in any case, that's the example of this. So the default shell in Solaris, according to this, is CSH. And then from that, we might launch Netscape, which was a web browser. And we might also launch Emacs, which is a text editor. I wonder if Emacs is loaded on here by default. I don't think so. It is. So this is a text editor kind of made for programmers.
Checking to see if the process ID was equal to 0 is just checking that it's forked correctly or not. It's not the actual process.
Okay, so it's the error code. If the error code was 0, that means it worked, and that's the child. That makes sense. So you don't actually get the process ID.
You'd have to call another method.
So why do they call it PID? Kind of bad variable notation.
Yeah.
Whatever. Doesn't matter. Important thing is just we understand that fork creates a second process. This guy allows us to know, are we the child or are we the parent? That's the punchline. Okay. So in any case, this is just showing an example of all the different processes that might be running on Solaris at the same time. These are user applications running right here. This init might have a login coming into the telnet daemon, which then turns into a session. Well, I don't know what the SDT, but this is going to be the shell program, which is running as CSH. We can issue CSH a command ls or cat. Cat spits out everything from a file. Here's another instance of CSH that's dealing with Netscape here. Okay, so this would probably be a local login. This would be a remote login through the telnet daemon. Okay, so just an example of a bunch of processes running on a certain operating system. Process termination lets the parent know through the wait command that it's done if it's the child. If it's the parent, process resources are deallocated by the operating system, child as well. If we're using the fork command, threads, everything was already allocated to the parent. Parent may terminate execution of child processes. So the parent's in charge of the child. You know, I brought you into this world, I can take you out. That That's where it came from, actually. It's computer speak. It's geek speak. So child exceeded allocated resources, so we can kill it off by the parent. Operating system can also kill it off through the super user account. Typically, by default, when you're out at a terminal, you do not have super user privileges. If you need to do something that requires super user privileges, you use the sudo, su command allows us to log in as the super user. And I don't think the Mac OS must not let you become the super user directly. You can run programs as a super user using a command called sudo. Okay, so this is doing something as the super user. So I can run ls as the super user. It's asking me the password, and it's showing me more stuff than just ls did. I think I could do ls.a though, and -a, that shows me the equivalent stuff. But regardless, if you need to run something as the super user without becoming the super user, you use sudo. All right, let's just keep going here. A couple minutes left, and we're not going to finish all these. That's okay, actually. We're coming on to something that's going to take some time anyway, so I'll just introduce it. So now we have this concept of inter-process communication. So we have a bunch of child processes running around that might need to communicate with each other. They also might need to communicate with the parent. Well, we saw an example of how the parent can become aware that a child has terminated through the wait command. Well, there's other tools for inter-process communication that allow us to actually send stuff between child processes. So information sharing, computation speed up. So we might have multiple threads or multiple processes where each one's going to take on a part of the problem, where those guys need to actually communicate with each other, letting them know my part is done, or here's this piece, I think it belongs to you, that kind of stuff. All right. So if you think about a whole bunch of people getting together to rake the leaves in the park, they might have some sort of communication with each other, that, I'll take care of, I'm done with my part, I'll take care of the playground, something like that. Okay, so some examples of when they're talking to each other. And then here's some ideas of shared memory and also message passing. So shared memory is a central part of RAM that all the child processes can write to and see from each other. So it's almost like a global environment, global variables that all children have access to. And then also message passing, which we direct communication to between child processes. All right, so I'll stop there. We'll go on this communication model thing next. So no homework. Have a good Thanksgiving. If you're traveling, travel safe, and I'll see everybody on Monday.